There is something wrong with the night sky. You wouldn't know it standing in your garden, head back, watching the stars come out one by one as the last light fades in the west. It looks right. A handful of bright ones first, then more, then thousands, scattered across the dark like someone spilled salt on black velvet. But something is missing. Most of it, in fact. Just try to picture the universe. Hundreds of billions of galaxies, each containing hundreds of billions of stars, all of it spread across a space so large that light, traveling at 300,000 kilometers every second, would take 93 billion years to cross it. Everything you can see, every star, every galaxy, every cloud of glowing gas, is 5% of what's actually there. The rest is dark. It doesn't glow. It doesn't announce itself in any way we've managed to detect. It's just there. Everywhere. Holding everything together in silence. We found it by noticing a number that didn't add up. In 1933, a Swiss astronomer named Fritz Zwicky was watching galaxies. Hundreds of them, bound together in a cluster 320 million light-years away. He measured how fast they moved, and the answer came back wrong. The galaxies were moving too fast. Far too fast for the gravity of the visible stars to hold them. That cluster should have flown apart long ago. The stars should have scattered into the dark. But they hadn't. They were still there, still together. Something was holding them that he couldn't see. He called it dark matter and went back to his desk, and the world moved on without him. 40 years passed. Then Vera Rubin sat down at a telescope and started measuring how stars move inside galaxies. Galaxy after galaxy, night after night. She found the same wrong number. Stars at the outer edges of galaxies. The ones that should be drifting slowly, far from the gravitational pull of the center, were moving just as fast as the stars near the middle. As if something invisible was wrapped around each galaxy. Something enormous. Our own Milky Way sits inside a halo of dark matter stretching 600,000 light-years in every direction. The galaxy in the photographs, the beautiful spiral of stars and dust, is just the glowing center of something far larger that nobody can see. We live inside it. Right now, as you lie there, dark matter particles are moving through you. Through the floor. Through the earth. They don't notice you. And you don't notice them. In 2006, two galaxy clusters collided. 3.8 billion light-years away. Two vast collections of galaxies passed through each other at 3,000 kilometers per second. When they met, the ordinary matter slowed down. Piled up. Heated to hundreds of millions of degrees and blazed in X-rays. But the dark matter kept going. Straight through. The two dark halos passed through each other like two ghosts through the same wall, neither one aware of the other. For the first time, we could see what glows and what holds. They're not the same thing. They had never been the same thing. Look up at Andromeda tonight if you can find it. A faint smudge, easy to miss. The light reaching your eye left that galaxy 2.5 million years ago, before humans walked the Earth. 1 trillion stars, all of them burning. And all of that light is 20% of what Andromeda actually is. The rest is dark, silent, and it is falling toward us. In 4.5 billion years, the Milky Way and Andromeda will meet. Their dark halos will reach each other first, merging slowly, quietly, long before any star gets close to another. The darkness finds the darkness and becomes one thing. What's left will be called Milkometa, a new galaxy, born from two. We still don't know what dark matter is. After nearly a century, after detectors buried miles underground, after satellites and telescopes and particle accelerators and decades of mathematics, it hasn't told us. It just holds everything together, the way it always has. And somewhere inside the small fraction that glows, something figured out it was there. That something is us. The universe was bright, but opaque, like trying to see through the surface of the sun. Then the temperature dropped just enough. Electrons and protons combined into hydrogen atoms for the first time, and light was suddenly free. It streamed out in every direction, unobstructed, across a universe that had just become transparent. That light is still traveling today. We can detect it, a faint, almost perfectly uniform glow coming from every direction in the sky. The oldest light in the universe. A photograph of the cosmos when it was 380,000 years old. And that photograph is almost perfectly smooth. Not completely. There are tiny variations, temperature differences of about 1 part in 100,000. Barely anything. A universe that was, to a startling degree, the same everywhere you looked. That universe produced this one. Somehow, from that near-featureless beginning, came hundreds of billions of galaxies arranged in a web of filaments and walls stretching across billions of light-years. The question is, how? While ordinary matter was locked in that bright, churning plasma, unable to clump together because the pressure of light kept pushing it apart, the dark matter was doing something else entirely. Dark matter doesn't interact with light. The intense radiation filling the early universe passed straight through it, the way it still passes through you right now. So while ordinary matter was being scattered and held smooth by all that pressure, the dark matter was quietly beginning to fall together. Gravity is patient. The tiny variations in dark matter density, those 1 in 100,000 differences, were enough. Where there was slightly more, gravity pulled in slightly more, which made the gravity stronger, which pulled in more. Over tens of millions of years, the dark matter began forming structure. Halos, clumps, filaments. The universe was building a skeleton. About 200 million years after the Big Bang, the first stars switched on. Nobody saw it happen. But somewhere, a cloud of hydrogen gas had fallen into a dark matter halo dense enough to pull it inward. The gas compressed, heated, and at the center of it all, nuclear fusion began. The first light in the universe that had been dark for 200 million years. Those first stars were nothing like our sun. They were enormous, hundreds of times more massive, burning through their fuel in a few million years. When they died violently, scattering the first heavy elements into the surrounding gas. The dark matter halos kept growing, merging, smaller halos falling into larger ones, carrying their gas and their young stars with them. This is how galaxies form, not in a single event or a collision. Through the slow, relentless accumulation of dark matter pulling ordinary matter inward over billions of years, piece by piece, every galaxy that exists sits inside a dark matter halo. The halo came first. The stars followed. In the late 1990s, a group of astronomers ran a simulation. They called it the Millennium Simulation, a computer model of a cube of universe 2 billion light-years across, containing 10 billion dark matter particles. They set the initial conditions to match what we know about the early universe, and let it run. The same distribution of galaxy sizes that we see when we point our telescopes at the real sky. The simulation had no ordinary matter in it, no stars, no gas, just dark matter, gravity, and time. And yet, it produced the skeleton of everything. Picture a spiderweb covered in dew, early in the morning. The threads connect at nodes where the drops are largest. Between the threads, empty space. That's roughly what the large-scale structure of the universe looks like, except the threads are hundreds of millions of light-years long, and the drops at the intersections are galaxy clusters containing thousands of galaxies. Our own Milky Way sits in a quieter part of this web, not at a major node, somewhere along a filament. The local group, about 50 galaxies, held together by gravity, drifting slowly through a universe that is mostly empty. The nearest large node is the Virgo cluster, about 65 million light-years away. Thousands of galaxies, all falling slowly toward its center. The Milky Way is falling toward it too. Very slowly. We won't get there for billions of years, but the pull is there. Quiet and steady. Everything is falling toward something. Only ordinary matter. Only the stuff. The universe that emerges doesn't match the one we live in. The filaments are wrong. The clusters form too late, in the wrong places. Galaxies don't look right. The cosmic web only appears when you include the dark matter. It was the dark matter that fell together first. That built the halos. That gave ordinary matter somewhere to fall into. Without it, the hydrogen and helium from the Big Bang would have drifted apart, never forming stars, never forming anything. The universe we can see was built on a foundation we can't. Think about what that means. The atoms in your body were forged inside stars. But those stars formed inside galaxies. And those galaxies formed inside dark matter halos. And those halos grew from tiny fluctuations in dark matter density 13 billion years ago, in the first few 100 million years after the universe began. Follow that chain back far enough, and the fact that you exist depends on dark matter behaving exactly the way it did. The invisible majority of the universe, silently accumulating in the dark for billions of years, building the structure that ordinary matter fell into, building the stars that forged the atoms that eventually arranged themselves into something lying here in the dark, listening. The universe built you out of itself. It just used parts you can't see. You are here, on a rocky planet, orbiting an ordinary star, sitting about 26,000 light-years from the center of a galaxy called the Milky Way. The Milky Way is not remarkable by galactic standards. A spiral galaxy, maybe 100,000 light-years across, somewhere between 100 and 400 billion stars. Middle-aged, settled. But what you can see of it, the stars, the dust lanes, the glowing clouds of gas, is just the surface of something much larger. The dark matter halo surrounding the Milky Way stretches somewhere between 1 and 2 million light-years in every direction, 10 to 20 times larger than the visible galaxy. Everything you've ever seen in the night sky, every star, every constellation, every smudge of the Milky Way on a clear night, exists inside a structure that extends far beyond any of it, invisible in every direction. We are deep inside something we cannot see. Right now, you are moving. The planet you're on is orbiting the Sun at about 30 kilometers per second. The Sun is orbiting the center of the Milky Way at about 230 kilometers per second. You are, right now, hurtling through space at nearly 1,000,000 kilometers per hour, tracing an enormous circle around a point 26,000 light-years away. One full orbit takes about 225 million years. The last time the Sun was in this part of its orbit, dinosaurs hadn't evolved yet. The time before that, complex life on Earth had barely appeared. The Sun has completed about 20 orbits since it formed, and the dark matter halo holds all of it together. Without the additional gravitational pull of that invisible halo, the Sun would be moving too fast for the galaxy to hold it. It would eventually drift outward, away from the center, into the dark. The stars at the outer edges of the Milky Way would do the same. The galaxy would slowly unravel. The spiral arms you see in photographs, those sweeping curves of stars and gas, exist because something enormous and invisible is holding everything in place. At the center of the Milky Way, 26,000 light-years from where you're lying right now, there is a black hole. Its name is Sagittarius, IH. It has the mass of about 4 million suns, compressed into a space roughly the size of the orbit of Mercury. Around it, stars orbit in years rather than millions of years, some of them moving at thousands of kilometers per second, whipping around it like a swarm of bees around something they can't quite see. We know it's there because we watched those stars. For decades, astronomers tracked their positions night after night, year after year, watching them trace ellipses that could only be explained by something enormous sitting at the center of each orbit. In 2022, we took its photograph, the Event Horizon Telescope, a network of radio telescopes spread across the entire Earth, working together as a single instrument, captured an image of the shadow cast by Sagittarius A's event horizon. A bright ring of superheated gas. A dark circle at the center where gravity prevented any light from escaping. For the first time, we could see the thing at the heart of our own galaxy. It sat there, 26,000 light-years away, surrounded by its dark matter halo, as it has been for billions of years, waiting, in a sense, to be seen. We had been trying to catch dark matter directly for decades. If dark matter is made of particles, and most physicists think it probably is, then those particles should occasionally collide with ordinary matter. Very rarely and very weakly, but occasionally. So we built traps. The Lux Zeppelin detector, buried 1.5 kilometers underground in an old gold mine in the Black Hills of South Dakota, contains 10 tons of liquid xenon, cooled to -100 degrees Celsius, surrounded by a tank of water 6 meters deep to shield it from cosmic rays. The idea, if a dark matter particle passes through the xenon and collides with a xenon nucleus, it produces a tiny flash of light and a small electrical signal. We would see it. We have been watching for years. The detector is sensitive enough to detect a single photon, sensitive enough to notice the recoil of a single xenon atom. And so far, nothing. This doesn't mean dark matter doesn't exist. It means we still don't know what it's made of. Each null result narrows the possibilities, rules out another piece of the map. The search continues. There are other candidates. Axions are particles so light they make electrons look massive. Proposed not to explain dark matter, but to solve a completely different problem in particle physics. They interact so weakly with ordinary matter that detecting one requires a resonant cavity tuned to the frequency at which axions would convert to photons in a strong magnetic field. Several experiments are scanning through frequencies right now, listening for a signal that may or may not come. Then there are primordial black holes, tiny black holes formed in the first fractions of a second after the Big Bang, from random density fluctuations before any stars existed. If enough of them formed, they could account for the dark matter we observe. The gravitational wave detectors, LIGO and Virgo, would be sensitive enough to detect the mergers of such objects. We haven't found those either. Here is what we know with certainty. Something is there. It has mass. It shaped the universe. It fills the halos of galaxies across the observable cosmos. It was present from near the beginning and determined almost everything that came after. And we don't know what it is. That's not a failure. That's where science actually lives, at the edge of what we can answer. Most of what we know about the universe was found by people who didn't know what they were looking for, following a signal they barely understood into territory where the old answers stopped working. Zwicky sat at his desk in 1933 with a number that didn't add up. We're still sitting with it. And somewhere down there, 1.5 kilometers underground in South Dakota, 10 tons of liquid xenon are waiting in the dark for something to pass through. Patient as dark matter itself. In 1998, two teams of astronomers were trying to measure how fast the universe was slowing down. That was the question, not whether it was slowing down. That seemed obvious. The universe had been expanding since the Big Bang, and gravity pulls things together. Of course, the expansion was decelerating. The only interesting question was by how much. They used supernovae to measure it. Type Ia supernovae, stellar explosions so precisely calibrated that astronomers use them as standard candles. A Type Ia supernova always reaches roughly the same peak brightness. Measure how bright one appears from Earth, and you can calculate how far away it is, know how far away it is, and you can figure out how the expansion has changed over time. Both teams were racing each other. Different telescopes, different methods, different supernovae. One would announce first. The other would confirm or contradict. They both got the same answer. The universe was not slowing down. It was speeding up. Take a moment with that. The expansion of the universe, the stretching of space itself in every direction, is accelerating. Galaxies are not just moving apart. They are moving apart faster every year. Whatever is causing this is working against gravity, pushing outward, and it is winning. We have no idea what it is. We call it dark energy. It accounts for about 68% of the total energy content of the universe. Dark matter is 27%. Ordinary matter, everything we've ever seen or touched or studied, is the remaining 5%. The universe is 95% things we don't understand. Two of them, and one is actively pushing everything apart. Albert Einstein predicted something like this in 1917. He was trying to construct a static universe, one that neither expanded nor contracted. His equations naturally produced a universe in motion, which bothered him. So he introduced a term, the cosmological constant, a repulsive energy built into space itself, pushing outward just enough to counterbalance gravity. Then Edwin Hubble discovered, in 1929, that the universe was already expanding. Einstein abandoned the cosmological constant, called it his greatest blunder. He was wrong to abandon it. Something very much like it appears to be real. Dark energy behaves almost exactly the way Einstein's term would have behaved, except instead of holding a static universe in place, it's accelerating an already expanding one. He invented it for the wrong reasons and threw it away. The universe had it all along. Here is what the acceleration means. There is already a horizon, a boundary beyond which the universe is unreachable. Galaxies whose light is currently reaching us will one day redshift into longer and longer wavelengths, grow dimmer, and eventually vanish. The space between us and them will stretch faster than any signal can cross it. The Andromeda Galaxy is close enough that it will merge with the Milky Way before dark energy tears us apart. But the distant clusters, the ones we can still see, will one day disappear from view. The horizon is shrinking. Slowly, but it's shrinking. Future astronomers, if any exist, will look up at a much smaller sky. Billions of years from now, the Milky Way and Andromeda will have merged into Milkomeda. The local group, our small collection of about 50 galaxies, will remain gravitationally bound. But everything beyond it will be gone from view. Those future astronomers will have no evidence that the universe contains anything outside their own island. No distant galaxies to map. No cosmic microwave background. It will have stretched to wavelengths too long to observe. No way to measure the expansion, because there will be nothing visible to measure it against. They will look up and see almost nothing, and they will have no way of knowing what they're missing. We exist at the one moment in cosmic history when the universe is still legible, when the evidence is still visible, when the full story can still be read from the sky. The evidence will not always be there. There's something quietly unsettling about dark energy that gets lost in the numbers. In quantum field theory, empty space, nothing, should be seething with energy. Virtual particles popping in and out of existence, contributing a constant energy density to space itself. Physicists calculated what this vacuum energy should be. The answer was wrong by a factor of 10 to the power of 100. A 1 followed by 120 zeros. The worst prediction in the history of physics by a comfortable margin. The theoretical expectation for the energy of empty space is so enormous that if it were real, the universe would have been torn apart in the first fractions of a second. Something cancels most of it out. We don't know what. The dark energy we observe is tiny by comparison. But it's there, and it has exactly the right value to accelerate the expansion gently enough that galaxies could form. Stars could burn for billions of years. Planets could cool. Whether that's a coincidence or something more, nobody knows. Think about what the sky will look like in 100 billion years. The stars will mostly be gone. The local group will drift through a universe that appears nearly empty, surrounded by darkness, with no visible evidence that anything else exists. And somewhere out there, stretched beyond any possible detection, the photons from tonight will still be traveling. The light leaving wherever you are right now will spend the next 100 billion years crossing a universe that has grown too large for any instrument to follow. The universe doesn't end. It just empties. And what we know now, the dark matter, the cosmic web, the 1998 supernovae, the xenon waiting underground, all of it will be unreachable to anyone who comes after. This is the only time any of it can be known. You're hearing it now. There's a limit to how far back you can see. Not because something ends there. Light just hasn't had enough time. Everything you've ever seen in the sky is old by the time it reaches you. The moon is a second behind. The sun, 8 minutes. The nearest star, 4 years. Andromeda is already ancient by the time you look at it. You never see anything as it is, only as it was. The deeper you look, the further back you go. That's all a telescope really does. It trades distance for time. The furthest galaxies we can see are more than 13 billion light-years away. Their light started traveling before the Milky Way existed, before the Sun, before Earth. And they look like it. They're not proper galaxies yet, just fragments, clumps of stars still trying to come together. You're catching them mid-assembly. Keep going back, and eventually there's nothing left to see. No stars, no galaxies, no atoms. Just a dense hot fog where light can't move freely. That's the cutoff. Not because nothing happened before that, because nothing from before that can reach you. So you stop trying to look directly and start reading the leftovers. The universe kept a record in the way galaxies are spread out, in the faint glow left over from the early universe, in patterns that don't make much sense until you realize they're echoes. There's one in particular. If you map the tiny temperature differences across the sky, you see a slight preference for a certain distance, roughly 500 million light-years today. It's not obvious. You have to dig for it. But it's there. It comes from a time when the universe behaved more like a fluid than empty space. Gravity pulled inward. Radiation pushed outward. So everything started to oscillate, like pressure waves moving through a dense medium. Then things cooled down. Atoms formed. Light was finally able to travel. And the waves stopped. Whatever shape they had at that moment got locked in, stretched over billions of years, but still there. You can see it now in how galaxies are arranged. A pattern from a time before stars existed. That's how you study the early universe. You don't observe it directly. You look at what it left behind. There's an earlier limit, one we're not even close to seeing past. Right after the beginning, something happened. For a fraction of a second, the universe expanded ridiculously fast. Not gradually, not gently. It just blew up in size. This is what people call inflation. Something smaller than an atom got stretched to astronomical scales. Any large irregularities got smoothed out, except for one thing. At very small scales, things aren't stable. Fields fluctuate randomly. You can't get rid of that. During inflation, those tiny fluctuations got pulled apart, stretched from microscopic noise into something large enough to shape galaxies. That's the strange part. Everything you see at the largest scales started out smaller than an atom. There's no picture of this, no clean observation, just a lot of indirect evidence that fits together a little too well to ignore. The universe is almost perfectly flat. The background radiation is almost perfectly uniform. The variations follow very specific statistical patterns. Take inflation out, and none of that lines up. And if you follow that chain forward, it ends up here. Atoms formed in stars. Stars formed in galaxies. Galaxies formed in dark matter halos. Those halos grew out of tiny fluctuations in the early universe. Keep going, you end up at quantum noise. That's not poetic. That's the actual chain. And there's one more thing people don't really like to sit with. If inflation can happen once, there's no clear reason it couldn't happen again. Not here, but somewhere else. Separate regions, expanding on their own, never interacting. People call that the multiverse. The problem is, you might never be able to check. That's where things stop being clean. There's a boundary between what you can measure and what you can only infer. We're standing right on it. Same situation as with dark matter. Same with dark energy. Most of what's going on, you don't see directly. You just see the effects. And that's probably as far as it goes. At some point, you run out of questions you can actually answer. Not because you stop asking. You just lose the ability to check. Up to a certain point, the process is simple. You build something. You measure something. You compare it to a prediction. Even when it's hard, it's still concrete. Then that stops working. No signal. Nothing new to measure. You're left with whatever already reached you and how well your ideas fit it. Inflation sits right there. It explains a lot, maybe a little too neatly. The universe is flat. The early light is almost perfectly uniform. The tiny variations follow a very specific pattern. Inflation ties those together, but you never see it happen. You just back it out from the result. And if you push past that, it gets quieter. If inflation can happen once, there's no obvious reason it couldn't happen elsewhere. Not here. Somewhere else. Separate regions. Expanding on their own. No contact. No exchange. No way to send or receive anything between them. If that's real, then what you call the universe is just a small part of something bigger. Not hidden. Just unreachable. And there's a difference. Hidden things can, in principle, be found. Unreachable ones can't. There's no experiment that bridges that gap. No signal you're waiting for. So you end up with ideas that fit everything you can observe, and still might never be confirmed directly. That's where things get a bit uncomfortable. There are limits to what you can know. Not because of technology, because of where you are. You're inside the system. Everything you learn comes from signals that reach you. And some never will. You've already seen that boundary a few times. You can't look past the early universe becoming transparent. You can't detect most of the mass in a galaxy directly. You don't know what's driving the expansion. And now, maybe, entire regions that never interact with you at all. It sounds like a dead end. It isn't. This is what it looks like when you get close to the edge of something real. You don't get a final answer. You get a line you can't cross. And you can describe that line pretty well. That's the position you're in. Lying here, on a planet you don't feel moving, in a galaxy you can't step outside of, inside a structure you can't see directly, in a universe that keeps expanding whether you watch it or not. Most of it is out of reach. Not temporarily. Just out of reach. And still, somehow, this much is clear. You know the age of the universe, give or take. You know roughly what it's made of, even if you don't know what those things actually are. You know how structure formed. That's not nothing. It's also not complete. And it probably never will be. If you go back to where this started, it wasn't a grand idea. It was a mismatch. Galaxies moving too fast. Something missing. That was enough to start pulling on the thread. And it kept going. Dark matter. Structure. The early universe. Inflation. Each step built on something slightly off. That hasn't stopped. Somewhere right now, there's another number that doesn't fit. Someone is staring at it, not quite understanding it yet. That's usually how the next step begins. But for now, this is where you are. In a universe that is mostly invisible, mostly unreachable, and still not entirely unknown. And you're here, somewhere inside it.